Now, before we study further, we shall discuss the various type of structural steel projects that are done in Australia. So for that, I have opened a website for by steelcorp.com.au, and they are like the very good steel structural, we can say, contractors in Australia. So we should open each and every building and we shall try to, understand what exactly are the different components of structural steel buildings, what are the challenges faced, and how, we can do that. Basically, understanding structural steel building components is the intent of, we can say, this particular video discussion. So we shall discuss each and every component like beams, rafters, cold form sections, purlins, girts, doors, we can say, or loading unloading panels. So these are the components that my intent is to discuss. So this is also a typical example where you can see this is basically the forklift that is usually used. So if we are talking about, we can say, this particular forklift warehouse, so we do need to ensure that whatever the loading of this particular grade slab, that has to be compliant. That is, this particular grade slab on RCC concrete grade slab on the bottom, that should be able to take the load from this particular forklift. Similarly, if we open the next building, next images, here you can see these pipes coming from, we can say, top to bottom. So if we are talking about these particular pipes, so these are known as the rainwater pipes. So, and this is basically the eave gutter. This is known as eave gutter. Let me just write it down here. So as I said, that basically eave gutter is the system where, if we're talking about this particular slope, this is the, we can say, building elevation. So whatever rainwater is coming, that shall be collected here in the eave gutter, and that shall basically be, we can say, transferred to the underground drainage. So this is known as eave gutter. This is known as RWP also, and we can say rainwater pipe. So this is usually, we can say, 150 mm in diameter, or in some case it may be lesser than that also, more than that also, but that 150 mm is the standard like diameter, which is, here you can see that this is going down the ground. So whatever is the building periphery, there must be a drainage at the bottom where this water is getting collected and then getting transferred to the main, we can say, underground drainage. So here you can see these are the rolling shutters that are, we can say, that is the standard that you already know. And in the this we had already discussed about the forklift and the we can say vehicular loading. So here we can see that this is the grade slab on the bottom. So this grade slab is like designed by, we can say, various standards. So one of the option is Cement and Concrete Association Australia, and that has an excellent manual which guides us on how to, we can say, design the grade slab on the, we can say, ground for this kind of loading. So that also we shall be discussing in a separate lecture, that how we can design the grade slab. And similarly, the major thing that you do need to do is that majority of the cases as a structural engineer, you may be, having an issue where you do need to design the grade slab as per the forklift loading. So forklift loading is like that also we shall be discussing in the grade slab lecture. But there are these, 2 to 3 different types of loading for which usually grade slabs are designed. Grade slabs. So one loading is the, we can say, area loading. So area loading is, the usually it is in the range of 30 kilonewton to 40 kilonewton. So that is one loading. Second loading is the point loading. So point loading is the case where, we do have to sometimes stack the material. So to stack the materials, we do have, very tall, we can say, storage panels. So that also, we shall be discussing in a separate lecture. But on the bottom of that, we do have a, we can say, rectangular plate or a square plate. So that square plate is putting a, we can say, point load on the rectangular, or sorry, on the RCC grade slab. and this is usually in the range of 150 mm by 150 mm, or it is sometimes rectangular also. And this loading here, it do depends on the number of floors that we are having. So uh, this point load is also in the range of, we can say, 25 kilonewton, or we can say 30 kilonewton. But the only problem is that the punching load governs the design in this particular scenario. So that also we shall be discussing. But as I said, that this is just a general lecture, as so that you can understand what exactly are the various components. Yeah, also like here you can see that how we can see sheeting is getting supported on these members here. These members, just so as you understand, we do have to install the sheeting. One thing. Now, when we are installing the sheeting, we do need some member. One is the structural steel member that we had already, considered here. The structural steel member is already there. But on the top of that, we do have to, use another members here. So these are, we can say, cold form members. Cold form members. And these are usually, we can say, uh, Z purlins. And, the when we are supporting the sheeting on the top, they are known as the purlins. Purlins. But the same member, when they are supporting the side sheeting, they are known as girts. GIRTS. So one of the challenges that that also we shall be discussing in the separate lecture is that how you can design the purlins and girts. In here you can see this is basically the girt. This member here, the horizontal member, that is that we can see here, that is the girt. And on the top of that, here you can see member on the top supporting the sheeting. So this member here, this is the purlin, and as I said, this is the girt member, and this member here, this is basically the steel column that is supporting, and this is basically the truss system arrangement that has been made to support the, we can say, roofing arrangement. So either this member here, this member is a single member, or as I said that the height is like quite high in this particular case, and the span must be very long. So what they usually do is that they make this kind of system to support the roofing. That is, these are the, we can say, structural steel members, and what they do is that they make this kind of arrangement, and then they design, take considering as a truss member. So instead of making a single member here, for optimize cost optimization also, we can say, so this kind of arrangement is made. So that also we shall be discussing. But the important thing that you do need to understand, rectangular RCC grade slab. After that, rainwater pipes. We do have to do the hydraulic calculations also, so that we can calculate that whether the eave gutter size that we are having, or whether the rainwater pipe, or whether the size of the underground drainage that we are having is correct or not. Australia being a very large country, we cannot say that rainfall is uniform across the country. We do have, we can say, dry area also, and we do have a very wet area where there are cyclones also. So we do have to correctly predict the calculations to find out that what exactly should be the size of this eave gutter. And if you're talking about the rainwater pipes, so let us say we do have a building here. So whether we do need rainwater pipes on each and every frame, or we can have rainwater pipe on alternate frames also. It all depends on what exactly is the requirement of the as per the rainfall intensity. So that is the one thing that we shall be discussing in the separate lecture. But I hope the rainwater pipes are clear to you. Eave gutter proposal is clear to you, and the difference between the purlins and girts, and how you can see this is the typical structural steel frame. So that is one discussion. After that, we shall be this is the inside of this particular, we can say, design and construction of industrial workshop for Hutchison and Pierce, agriculture supplier in NSW's Riverina. So if we're talking about this industrial steel warehouse in New South Wales, basically you can see that they are the supplier of the agriculture equipment. So if they are supplier of agriculture equipment, so whatever tire load that is coming on this grade slab, that must be huge. So we do have to ensure that this particular grade slab does not get cracked when this particular loading is being, getting transferred on the grade slab. And here you can see a thin line also. This thin line is basically the joint, and this joint is usually the, we can say, I can say construction joint, or we can say contraction joint also. So this grade slab design is a very, a big uh, challenge in itself, and there are many structural engineers who do grade slab design only. So we shall, as I said, that I shall explain each and everything in great detail, but just to, coming back to this intent of this lecture, I shall be discussing about the structural steel parameters that we are having. So as I said that this is the particular steel column that we had already discussed, and this is the, we can say, portal frame that has been constructed. And here you can see that there are no as such vertical members here. What the designer has done is that he has taken only, he or she has taken only this kind of system. Now, we shall be discussing in a separate lecture about this. But if we are taking about this particular member here, if we, if we take a straight member also, then there is a very less force getting transferred here. Majority of the forces are usually transferred in the diagonal members are also. So that might have been the intent of not taking any kind of vertical members here, or taking only diagonal members when talking about the portal frame design. After that, as you can see that this system is transferred to the structural steel column here. Now this structural steel column here, that is not the hot rolled section that is usually available in the market. That is a built up section. So this built up section, as I said, is the section which is made by welding of 3 different plates. So what they usually do is that they take these 3 different plates and then they weld it together. And on the basis of that, on the basis of the bending moment requirements, we can simply size it. So here you can see that it should be in the range of 900 mm approximately. And this is a uniform section, that is, it is not varying along the height. In many cases, what the designer usually do is that they vary it something like this. So the intent is that the bottom is considered as pinned connection. So that is, all a completely different discussion, that if we are taking the bottom of support as pinned, then bending moment is something like this. The bending moment is something like this. That is, it is 0 at the bottom, but it is maximum at the top. So on the basis of the bending moment requirement itself, what the designer usually do is that they size the this particular structural steel column. Minimum, it is usually in the range of 300 mm at the bottom, and it may go as high as, we can say, 1250 or 1600 mm also, depending on the height. So the difference between, as I said, pinned and fixed connection. Fixed connection, it is something usually taken like this, because the bending moment profile in this particular case, it is usually in the range of like this. So whatever is the bending moment at the bottom, that bending moment is usually at the top also. So that is the, we can say, difference in the fixed connection and pinned base plate connection. So when we are talking about the fixed base plate connection, something look like this. That is, we do have 3 bolts here, in total 5 bolts here, and 5 bolts at the bottom. This is the fixed base plate connection, having capacity to transfer the bending moment at the bottom here. So if we are having this kind of base plate here, our bending moment profile is something like this. But if we are having this kind of system where we do have only a pinned base plate at the bottom, the pinned base plates look something like this. That is, we do not have any kind of bolt outside the flange. We do have all the bolts inside only. So that is basically the pinned base plate connection. and this is basically the fixed base plate connection. So I hope that is clear to you. And as I said that, as I am predicting here, this system here, this is fixed at the bottom. So that is why you can see a usual same straight profile. After that, here you can see that these are the fly bracings. So you can see how the girts here are basically tied to this particular structural steel column flange with the help of these fly bracings, and these fly bracings are usually L angles. So if I draw this in plan, so let us say this is basically the inside and this is basically the outside. So here we do have this girts here. So outside of the girt we do have the sheeting. So what they usually do is that they tie this bottom flange, or we can say inside flange of the structural steel column with these girts here. So this fly bracing is to basically, we can say, support the structural steel column and to ensure that the capacity of the structural steel column is increased, considering it as a partially supported wherever we are providing the fly bracings. So the effective length along the minor axis decreases when we do provide this kind of fly bracing system. And at the same time, the design of this girts, that is also done as per the Australian standard, and we do have like various suppliers such as Stramit, and Stramit is a supplier that usually do have a we can say capacity tables also. That is whatever the wind load is coming, on the basis of that they do propose the size of the girts or purlins. And the bending moment profile for, we can say, these girts here, it is usually in the range of something like this. That is the bending moment, it is not simply supported, it is, we can say, continuous, taken as continuous beam. So whenever we are designing the girts, we do consider it as a continuous rather than simply supported. And we do have to consider the local wind pressure calculations, that is the coefficient is higher as compared to the global, we can say, wind pressure coefficients. After that, we can consider the this particular aspect also, that is a crane loading. So this crane loading itself, although we can say that it is taught in our universities in our graduation or post graduation, but still the concept is not clear unless and until you have designed a practical we can say crane girder or gantry girder. So if we're talking about a difference between gantry girder and crane girder, this yellow beam here, this is a box beam profile. So usually this box beam profile, or it is something like this. That is, we do have this web plate, we do have this web plate, we do have a flange plate on the top, we do have a flange plate on the bottom. So this is basically this particular profile, and this is known as the gantry girder. So this gantry girder is basically resting. It is usually rested on the crane girder. So this beam here, this is basically the crane girder. So if we want to make a single line diagram of it, basically it is drawn as something like this. So here you can clearly see that wherever this small steel beam is constructed, how the designer has added a stiffener here. The intent of the stiffener here is to increase the shear capacity of this particular, we can say, crane girder supporting structural steel beam. As there is a very high amount of shear force that is traveling, so that is why designer has added a, we can say, stiffener here, that is also known as intermediate transverse stiffness or simply transverse stiffness also. And how this structural steel beam, what usually do is that wherever there is a discontinuity in the load path, or we can say majority of the load is getting transferred to this particular flange, what the designer has done is that he or she has added two more stiffeners here, so that under the composite this particular steel flange and this particular steel flange, they compositely behave against the loading of this particular we can say crane that is acting on the top. So that is the intent of these particular stiffeners here and this particular steel girder here. So, understanding components is a very important thing. And here also you can see that wherever, this particular uh, on the structural steel beam where these system is coming. So here you can see that designer has added two stiffeners here. So that is very much required because there may be a failure of the local buckling if this particular stiffeners are not provided. That is under the loading action. What may happen is that let us say this is the particular structural steel beam and these are the, we can say, flanges. So it may happen that there may be a temporary rotation here of this particular flange if the stiffener is not provided. So that is the basic engineering considered in the design of this particular warehouse. And on the top, if we want to see here also, you can see that how they have provided these fly bracings on every alternate purlin. They have not provided the fly bracing on each and every purlin. So this purlin here you can see that we do not have any kind of fly bracing here, but we have provided only fly bracing at this particular purlin. One of the reason why this has not been considered, it might be that this spacing and this spacing, it might be different. So if a designer want to provide the fly bracing from this particular point to this particular purlin, it is not, might not be coming straight, but here you can see that it is coming straight. Similarly here, after leaving the one purlin, they have joined the fly bracing at the alternate panel. So that was the basic engineering philosophy of these industrial steel warehouse design. These are known as basically the end wall columns or gable columns or wind columns also. Basically the philosophy is that, let us say this is the building that we do need to design. So what we usually do is that we do consider these as the main portal frames. So if we this is the plan. So if we draw this particular, let us say T1 in elevation, it looks something like this. But the problem comes, when we have to make portal frame here and here. We do not have luxury to provide only a portal frame like this, because ultimately the span is usually in the range of, let us say, 30 meters. So we do have to support the sheeting also. So to support the sheeting, what we usually do is that we do provide intermediate columns here, so that the span of the girts that we are making, that is supported. So that is why they are known as the wind columns or gable end columns, so that these girts that can be simply supported and this sheeting is stable. So unlike these columns which form a part of the lateral moment resisting frame of the complete building, these end wall columns only have a purpose of supporting the side sheeting, or a very we can say small percentage of stiffness may help us in we can say stabilizing the building against the earthquake or wind. After that, this is one more discussion that is very important. Here you can see that these are the cross wires. So these are basically the tensile rods. And when we design the buildings in, we can say, moderately or low earthquake seismic zones, in those buildings, we do have luxury of providing this kind of system where we do provide the bracing in the form of a very small wires. This is usually in the range of 16 mm or 20 mm solid wires. They do not have any such hollow inside, and they are simply stretched at the ends. So we can say that these are basically the tensile members which ensure the stability of the building against the wind and earthquake. But when we're talking about the bracings in very high seismic zones, so I've seen in New Zealand also some of the buildings have a system something like this. But if I am an engineer and I have to design the let us say this is these all four columns that we are having here. So 1, 2, 3, and 4. So let us say if I have to provide a bracing arrangement here, I shall ensure a very stiff arrangement of the bracing here. So that in the case of an extreme earthquake, if there is a stress reversal of the forces, which is usually there in the case of an extreme earthquake, so the stress reversal usually happens. So it may happen that these members may face a very out of the plane stiffness or out of the plane forces. So what I in my structure, what I usually do is that I do provide either in the form of, we can say, I sections, these bracing members, or C channels, or if the span is very less, I do provide angles also, so that they do have some capacity to take the compression forces also. In these kind of bracings, what they usually do is that they do simply provide an tension beforehand. So these are usually stretched out of the limit. So when the stress reversal happens, these rods become free and stop taking any kind of load. But again, when tension comes, it becomes active and they do again take the tension. So I'm not saying that this is wrong, but every engineer has his own thought process. As I worked in areas where there are a lot of earthquake forces, so I am much more comfortable considering this approach. Engineers who have worked only in the areas where there are moderate earthquakes or low earthquakes. In those areas, it is okay to consider these kind of bracing, not in the high seismic zones. And again, that is my point of view. So I hope this is clear to you. And here you can see that how the this uh, maintenance worker here, that is basically lifting this particular, we can say, weight with the help of this particular crane. And here also you can see that 10T is written on the top. So 10T means that the capacity of this particular we can say crane is 10 metric ton, or we can say 10,000 kg. And this is the power panel of this particular we can say crane, modular crane. So I hope the discussion is clear to you. We can open other pictures also. So here also we do have a beautiful image showing how they have designed. Yeah, this was the discussion that I wanted to have in the earlier lecture with you. Here you can see that basically this particular crane, we do have this rectangular housing here. So this rectangular, basically what is happening here is that this crane girder has two wheels here. So it must be having a wheel inside this particular, we can say, uh, supporting system here. And basically the loading action that comes from basically the point load is considered here, and then after that the point load is transferred on these two wheels on this particular support and two wheels on the other support. So in total 4 points we do transfer the load. And then after that, here you can see that the danger live rails is kind of written because there might be some electrical current in here. So that is why they have taken the precaution. And here also you can see that these are the cross bracings. And it should have been tightened as per my experience, but here they are sagging a little. So it is always better to, as I said, that to provide a strong members, or at least tighten them fully, so that at the time of the earthquake they do, or at the time of the extreme wind, they do perform as per their design considerations. So here you can see that fly bracings are provided at every alternate panel. These are, as we have discussed, are the crane girders and gantry girders. This is basically the portal steel truss system that we have already discussed. And on top of that, one more thing that I like to discuss is that they might have provided the insulation sheets also. So these silver color sheets, these are the insulation sheets which ensure that at a time of the, we can say, extreme summers or winters, the temperature does not affect the inside. So that is why insulation sheets are fixed at the top. Here also you can see a very strong grade slab that is fully supporting this particular agricultural equipment. So after that we can see more pictures here. So here also it is more or less same only. Yeah, here also this is one more image showing how the crane usually transfers the load via two wheels. So here also these are the two wheels, And this is basically, this already we had discussed the crane girders and gantry girders. This capacity is 10 metric ton. And these are basically the rolling shutters. Now, the importance of the rolling shutters as an engineer is there that this is basically an opening for us. So under the case of opening, basically what may happen is that the more the area of the opening, the more the wind load that we do need to consider. You know, if a building is completely sealed inside, there are no as such windows, there are no as such doors. The wind load is minimum in that particular case because CPI is the minimum. But in a case where we do have these large, rectangular openings, that is, we do have in this particular view, let us say, we do have 1, 2, and 3 rolling shutters. So these rolling shutters, now that is, the decision of us that whether we shall consider them as closed at a time of the cyclone or extreme winds, or we shall consider as an open at a time of cyclone or extreme wind. In the code also it is written that I think in AS 4100 part 2, and as per my experience also, if there are openings, we do have to consider them open. So we cannot guarantee that, at a time of the extreme winds or cyclone, there must be some maintenance worker here who shall be closing these rolling shutters, risking his or her own life. So that is why, we do have to ensure that whatever opening is there, that may open, and the wind may come inside and may put extra pressure on these particular structural steel frame. So one more thing that these are usually mechanically operated rolling shutters. So there must be a push button here. With the help of that, these rolling shutters may open or close. So I hope this project is much more clear to you now. Yeah, after that, we had already discussed that it is in New South Wales, and the value of this particular project is in the range of 750,000 to 850,000. And the area is approximately 51.5 into 18.5 into 11.5. Now I just want to discuss with you the thumb rules also. I'm not sure, thumb rules are like standard calculations that we engineer use to estimate the structural steel that is utilized and what exactly may be the cost of the building. So as a contractor, you do have to cross verify or estimate. So in our case, the area is approximately 51.5. So 51.5 into 18.5, we can see that the total area is approximately 953 square meter. And if we're talking about, if let us say, if we want to estimate how much structural steel shall be utilized in this particular building, so the simple thumb rule is that we do have to multiply this with either, we can say, as this is a very regular span building, because 18.5 is a regular span, it is not a very large span. So we can say that structural steel approximately shall come in the range of 30 kg per square meter. So if we are talking about let us say the thumb rules, basically if you are in US or in countries which are using in the range of per square foot, the approximate structural steel tonnage is in the range of 2.5 kg per square foot to 3.5 kg per square foot. 2.5 might be the case where the wind load is very less, and 3.5 to 4 kg also might be the case where the wind loads are moderate, and it may go as high as 4.5 to 5 also, where the wind load is very high. So in our case here, we can see that this is a regular structure, so it might be in the range of 3.5 to 4 kg per square foot, which comes out to be approximately 44 to 45 kg per square meter. So whatsoever is our area, we can simply multiply it with 45 to find out the approximate value of the structural steel that is used. So 51.5 into 18.5 into, we can simply multiply it with 45. So in total, we can say approximately 45,000 ton structural steel is approximately used. We can reduce it to 40,000 also. We can reduce it to 45, increase it to 45,000 also, depending on the usage. So if we consider it as 45,000 kg structural steel is used in this particular building. After that, if we want to calculate the costing of this particular, we can say, uh, building here. So approximate cost of the structural steel in Australia per kg is in the range of $8 to $9. Now this value is like 2 to 3 years old, I can recall, but it might have increased to $10 per kg also. So what we can do is that we can simply multiply it with $10. So the cost of the structural steel itself is in the range of 450,000. So after that, we do have to install or purchase the crane also. We do have to do this particular, we can say, grade slab also on the bottom. We do have to construct the foundations also. We do have to install the rolling shutters also. So that cost also like comes in the range of, we can say, 1.6 to 1.6 times to almost 1.8 times also. So if we multiply this, whatever the thing that I'm trying to convey here is that the structural steel cost is a very, we can say, factor that contributes only to 50 to 60% of the project cost. Rest of the cost is, as I said, the cost of the rolling shutters, the cost of the crane itself, the cost of the insulation, the cost of the sheeting, the cost of the grade slab that is installed on the bottom, the cost of the civil foundations, the foundations that we do need to cast on the bottom. So considering all of those factors, or we can say consider the cost of the drainage also. So considering all of that, we can simply multiply 450,000 with, we can say, 1.8. So it comes out approximately in the range of 800,000. So that is approximately the cost of this project that has been considered here. So as I said, that is a thumb rule, and that I also usually use to estimate the tonnage. So the more these kind of extra things are required, the more the overhead costs are there. Overhead cost means the cost of the civil foundations or the cost of the other kind of works. Now in this particular case, where this is basically project is in St. Catherine of Siena Catholic Primary School. So sports cover design and construction of St. Catherine of Siena Catholic Primary School in Geelong, Victoria, Australia. So in here you can see that they have installed this particular steel beam and curved structural steel trusses. And on top of that, they have installed the Z purlins, sheeting, eave gutter, rainwater pipes. So let us just, see these pictures in detail and discuss. Now, if we zoom into the pictures here you can see that this is basically the eave gutter that is installed on the top. And from that, we are basically, collecting the water with the help of the rainwater pipes that are basically clamped on the structural steel members. And after that, here also you can see that this is basically the, you can say, tie member itself that is provided. So the curved truss profile is basically provided on the top. So if we want to zoom into a photo here, so yeah, this is also one of the photo, and here you can see that this is basically the structural steel built up column that is made with the help of the plates. And here also you can see that wherever this truss is getting supported, we do have provided the additional stiffener here so that the flange does not get locally buckled at a time of, we can say, extreme forces. And here also you can notice that how they have provided a closure plate also on the top. And after that, you can see these are the Z purlins that have been provided on the top, and they are supported with the help of this, we can say, truss that is made, and with the help of this fly bracings. And here you can see that fly bracings have been provided on each and every panel here. It is not that fly bracings are not provided for the alternate panels. So it might be the case as, this is an open wind structure. So there might be we can say, a lot of bending moment requirement that might be coming for the wind stability. So that is why the designer might have provided a fly bracing on each and every panel. So here also, you can see one some other views here. So this is simple, is also like quite we can say a system that is simple. So what the designer has done, this is a steel column, this is a steel column, and they have simply make a curved truss with the help of this, and a truss with the help of this. And the wind load that is coming, that is considered as per the open structure. So as the wind is free to move inside, and wherever it is getting supported, the designer has provided we can say stiffeners here. And as I said, that on the top they have provided the Z purlins. There are no as such girds here because there is no as such side sheeting requirements. So whatever purlins that have been made here, so they are basically, we can say, fixed with the help of the screws that are installed on the top. So usually what happens is that, let us say this is the structural steel profile. What we usually do is that we do provide a plate on the top, and whatever Z member is coming, we do install a bolt here, so that it is ensured that the connection is done proper. And if we want to make a zoomed in view, let us say this is the plate, this is the truss profile, and let us say this is the structural Z profile, and we do provide a bolt here to fix this. So that is the system that is usually considered to fix the Z purlins, and on the top of that we do provide the sheeting arrangement, and this sheeting arrangement is usually fixed on these Z purlins with the help of the screws. Now these screws are the one that needs to be selected carefully. In the areas where there are cyclones, we do use anti-cyclonic screws. So anti-cyclonic screws are a little bit different than ordinary screw because they ensures that in the case of an extreme wind, sheeting does not get disjointed from the structural steel member. In majority of the cyclones that cyclone failures that have happened, in majority of the cases, structural steel members are not that much damaged, but sheeting is usually uplifted. Why? Because the screws that are provided, that get unstable, or it may simply get disjointed from the structural steel member. So that is why anti-cyclonic screws need to be installed. They do have a different kind of head at the top, so that head ensures that you know uh, the sheeting does not get separated from the structural steel member. So that is the basic thought process of the sheeting, purlin, skirt, fly bracing, structural sheet member, and the curved truss profile that has been selected. Now, one more thing, that I'm doubtful here is that the designer has provided the fly bracing here in all of these, members here. But when we're talking about the intermediate area, the designer, yeah, inside also designer has taken the fly bracings in all the, we can say, for all the bracings here. So this fly bracing is very important because when the wind shall strike from this particular face, this curved truss may have a capacity to get torsionally buckle. What I'm saying is that, let us say this is the curved truss here, and these are the purlins here. So what the designer has done is that he or she has provided these fly bracings. Why? Because what may happen is that at the case of an extreme wind, this we can say truss member here, it may simply rotate also, because at the case where there are column, it may it may support, but where there are no as such supports here, so this truss may bend also at a time of the extreme wind or cyclones. So that is why designer has provided the fly bracings at all the members so that this member does not get bent. So I hope this project is also now clear to you. After that, if we want to calculate or cross verify the costing, so as you can see that there are no as such girds inside, there are no as such fancy members that are coming. It is just a simple steel structure. So what we can do is that we can consider approximately 30 to 35 kg per square meter as the structural steel cost. Sorry, as the structural steel consumption. So the area of this particular shed here is 39 into 36. So the area comes out to be approximately 1404, which we can multiply it with, let us suppose, 35 kg per square meter. So this is the approximate structural steel that is used. So we can say that approximately 50,000 kg is used here. So if we multiply it with, as this project was constructed in 2021, at that time, I think the structural steel cost was in the range of $8 per kg, 8 Australian dollar per kg. So we can multiply it with 8. So approximately we can say that our cost comes out to be $400,000. So $400,000. On top of that, we do have to construct the foundation also, and we do have to do some work of this particular, we can say, play area also. So we can say that overall the cost that is written here, that is justified. So it may happen that 39 into 36, that may be multiplied with 30, because it is a very regular building. So if we multiply it with this, so we can say that approximately 350,000 might be the structural steel cost, and 100,000 might be the cost for the, we can say, sheeting, for the foundations, and for the play area that has been installed on the bottom. So that is the basic understanding. And here they have written the brief also, and that is like quite, we can say, good for your knowledge. So here you can see that the and primary school and encompassing a two-story 1,300 meter square administration building. So 1,500-meter covered outdoor learning area, which they name it as COLA. So 1,500-meter square area was thought of by the architect. The scope of Steel Corp contractor was to uh, make a 39 by 36 meter wide with 60-meter radius roof pitch. So the roofing is made with the help of the surf mist color bond sheeting that is also like quite easily available in Australia. Roof featured wonder glass skylights in each of the 5 bays for additional light penetration. Now, if we're talking about the wonder glass skylights, now this might be a little bit confusing to you, but let me just show the photo here again. In this photo here, you can see that how the light is coming inside. Here, this is basically known as a skylight. So the purpose of skylight is to ensure that it does not get completely dark. And there are these different vendors in Australia that manufacture these kind of, we can say, skylights also. So as I said, skylight, the only intent is to ensure that at the bottom it does not get dark, and there is a sense of openness also. So I hope the skylight concept is clear to you. After that, supported by hot tip galvanized web truss and universal beams. So the good thing is that they are not making that with the help of the plates. This is a standard universal beam that is available in Australia. After that, the structure includes 900 mm overhanging eaves on all sides for additional weather protection. Now, overhanging eaves are the one that has been that can be seen here. So if you're talking about the 900 mm, this is the 900 mm eve that the website is referring to. And one more thing, that they have galvanized the web truss and universal beams. Why? To ensure that it does not get corrode. So for the corrosion protection, they have galvanized this whole particular steel structure. And as I said, that galvanization itself add to $3 to $4 in the costing. So we can easily say that the rate should not be less than, we can say, $10 per kg if we're considering the galvanization also. So challenges that they had considered was that the 900 mm diameter core drill which cut right through the rock and soil. So what they're saying is that for the foundation they have encountered the very rocky strata. And here you can see that 1, 2, 3, 4, 5, 6, 6 here and 6 on the other side. So that is why they're talking about the 12 holes. So to overcome this, team switched to a tougher 900 mm dia core drill which cut right through the rock and the soil. The striking curved truss design was the biggest challenge considering more complex fabrication requirements. So yeah, overall curved truss fabrication is difficult. But at a time where we do have Tekla software or we have Autodesk Advanced Steel software, we can simply plan each and every joint. Fabrication has now become a very easier job. So yeah, that is a standard, we can say, discussion here. So I hope this project is also now very much clear to you. So similarly, we can discuss about the other projects also. But as I said that, the main intent here was to make it clear of what exactly are the different components and different kind of buildings. So here also, you can see one more example here: design and construction of weatherproof sports cover for Doonside Technology High School in Sydney and New South Wales. So here also you can see the how the fly bracing are simply propping out from the truss arrangement. So the intent here was to, what they have done is that they simply hidden the trusses with the help of the side sheeting. So if we remove this, sheeting here, the same truss might be constructed here also. That is the truss that we are discussing in the earlier buildings also. But on the top of that, what they have done is that they have installed the sheeting to hide this particular truss. But the main problem comes that, you can see the fly bracings here. So these are the fly bracings. So obviously they cannot, they has to come out of the uh, sheeting arrangement. So this is also like more or less the same principle only. And the scope here also we can discuss that the approximate size was 42 meter by 40 meters. Basically, what they have done is that why they have provided the sheeting here also. They have provided the sheeting here also to ensure that birds do not come inside and rest on these particular steel trusses. That is a problem. Here also you can see that how they have mentioned that to discourage birds from nesting in the open truss sections, because what they usually do is that the bird may sit here or the bird may sit here or they may make some nest also. So to avoid that, what they have done is that they have closed that with the help of the sheeting arrangement. So obviously, uh, that is, we can say, a different practice that has been considered. And I must say that this is quite common in the open steel structures. So we can see their scope also. The scope is simple, challenges are also simple. So similarly, we can estimate the costing here also. So approximately it is 42 into 40 meter. As the truss system is simple, we can simply consider 35 kg per square meter. And considering this project is in March 2023, so we can consider $9 to $10. So we can multiply it with $9. So approximate cost comes out to be 530,000. That is the same cost here. That is $600,000 dollars. So I hope the thumb rules are also now clear to you on how to approximately calculate the structural steel usage here in Australia. So you can go on discussing about the different kinds of buildings here. So equine buildings are also like quite common in Australia, where obviously they do have to make houses for the horses or equestrian staff. So this obviously it is a very beautiful building, I must say. It is quite different because of these the wooden panel doors that have been installed here. So the scope of Steel Corp was to construct 3D structural drawings, fabricated hot dip galvanized steel package consisting of purlins and girts, and they want to make world-class stallions, and breeder farm begin to outgrow the previous facilities. So obviously, horse breeding facility they want to make, and for that, they have constructed this particular uh, building. Obviously, might be due to the security reasons, they have not taken any pictures from the inside. They have only taken the pictures from the outside. Obviously, because this is not a very uh, this is a very expensive business prospect, horse breeding. So if we want make this particular building. I must say that for 65 by 13 meter of a barn complex, the cost is very high. Uh, they might have, this might be in a, we can say, a very remote area. So here you can see that if you want to calculate the overheads also, that also might be quite high in this particular project. So if we multiply 65 with 13.5, and we can multiply it with, let us say, 35 kg per square meter, and if we multiply it with we can say, let us say, $10 per kg, so the costing only comes out to be 300,000. But here you can see that is in the range of 700,000 to 800,000, because as I said that overheads are very high when we're talking about the making these kind of buildings in the remote region such as Macedon Ranges, Victoria. And they might have done a little bit different also in this particular project. Here you can see the steel sliding door tracks were made, or we can say something different was made for the horses inside. That is why the costing is very, very high. So instead of the standard costing, if you multiply, because structure steel tonnage cannot go beyond 40 kg per square meter, let us say the highest number. So here you can see that the costing per kg, they have considered approximately $20 per kg. Only then the number is matching. So the costing here in the remote region has been shoot up to $20 per kg, considering the remote area. So that is also a very important thing, that it does not matter that whether your project is in main Melbourne city, or we can say uh, or a moderately occupied region or a remote region. The costing is different in all the three areas. So as I said, that structural steel cost may be same, but the overhead such as transportation, placing, obviously we have to move the staff there also. We have to arrange for their accommodation. You have to arrange for their transport. Considering all of those factors, the overhead cost becomes very quite high. So you can refer to their website. They have other projects also that you can see and learn, and how exactly have they made them.